lectures on project. So, welcome back to our video lectures on projective geometry. Today we will enter a new chapter, and this chapter will keep us busy until the end of our class. We will talk about other geometries. Geometries that you find as a substructure in projective spaces, projective planes, projective lines, and we will see that many things we are already used to, like the usual Euclidean plane, but also more exotic things like the hyperbolic plane or spherical geometry will turn out to be substructures of projective geometries. To enter that topic, it's a good starting point to have a solid understanding of the role of complex numbers in geometry, and for that this first video slot will be about the complex projective line. And usually in the normal classes I give several lectures on that topic. I condensed this now to what I would call a kind of survival package, where I want to show you the most important effects that will be of relevance later on. So let us start with our CP1 survival package, and let me start with a little repetition of what we already had. These parts here should look familiar to you. It's what we did when we were talking about general projective lines. So we are for a moment at a general field K, and the construction of a projective line over that field was, well, the usual thing with homogeneous coordinates. We start with a two-dimensional vector space, we take away the zero vector, and we identify scalar multiples from that field where we don't allow zero multiples here. And if you do so, you can say, well, essentially each point can be represented in a kind of standard embedding, like you have an x and y, and you go to an altitude of y equals 1, and there you can find essentially each point of your projective line, except for one point. This one point has the coordinates 1, 0 with identified scalar multiples, which plays the role at infinity. So you can consider this space KP1 as, well, all elements of the field K, and you take a union with one point at infinity. What we also had when we were talking about one-dimensional projective spaces, we introduced projective transformations, which were multiplications of the homogeneous coordinates with a non-degenerate 2x2 matrix. So now we want to go to a special case where we set the field K to be the complex numbers. And for that special case, I want to focus on several effects that will be of importance later on. So one of them is what you already saw here. We have this one point at infinity. I want to really give you a geometric interpretation of this one point at infinity. We saw that you have these 2x2 matrices as transformations. I also want to give you geometric images of those. And, well, if you have these 2x2 matrices, as in any space of projective dimension 1, the images of 3 points, so you have a pre-image and an image pair, and you have given that 3 times, determines a projective transformation, and we will make use of that. Already in our last lectures, we got a glimpse of stereographic projection, and stereographic projection plays a major role when it comes to the complex projective line. We will see that. And circles play a very special role in the context of the complex projective line. And there is one last point I will talk about. Over the real numbers, we have seen that there is no non-trivial field automorphism, but this is no longer true for the complex numbers, and I want to show you what this non-trivial field automorphism means geometrically. So, two of those points, I want to take them apart and don't want to dive into much depth here. We already saw that 2 by 2 matrices determine transformations, and that if we have such a transformation, it's determined by 3 points. I don't have to explain that again. We already had that when we were talking about CP1, but I will use it later on. So let me take the first points on which I will fix, which is this one point at infinity and the stereographic projection, and give you an image of what is going on there. To do so, I will first step back for a moment and come back to stereographic projection as we had it in our contexts earlier on. And this happened when we were dealing with the real projective space and the real projective line. You remember in our video lectures about the conics, I showed you that the border of a conic, the line of which a conic consists, can be considered as a one-dimensional projective space wrapped up into a circle. So already there, this process of wrapping up the projective line with its point at infinity to a circle was closely related to stereographic projection. And here, as an example of a conic, I've taken a circle, and on that circle we identify one point. It really doesn't matter which point we take concretely, but the only thing that matters, it should not be a point where it touches the line. And from that point we project the border of the circle to our line, and this essentially gives us a one-to-one correspondence where each point on the line gets identified with one point on the circle. Except for one point on the circle, all of them are met. There is one special point, the projection point itself, that plays a special role because it is not hit by any point from the line, but it plays the role of the point at infinity, because if you move this point far out here, the corresponding projection will more and more approach this point at infinity, and so you see a kind of natural picture of the projective line on the circle with even the point at infinity. So it's a kind of compactification of the projective real line. And we learned we can do that for any conic. Now something very similar to that happens in the complex space. And here I've drawn a picture of stereographic projection for the complex line. And for that, the role of our real line here is now played by the plane of all complex numbers. So I take the complex numbers. So you remember a complex number consists of a real part plus an imaginary part. And I can consider these numbers here as points in a two-dimensional coordinate system. So for instance, in that picture, assume that this here is the real axis and that this here is the axis that corresponds to the complex line, and by that you get whole plane as the complex numbers, and each point at this plane here is mapped to a sphere through the north pole as an eye point of the sphere. And also here you get a one by one mapping of the points on the plane to all points on the sphere, except for one special point, the point at infinity. And by that, this sphere here is a nice representation of our space CP1 of all complex numbers together with the point at infinity. And to get a little bit better understanding and three-dimensional picture, here you see the whole situation rotating, and you see how this really takes place in three-dimensional space, although our projective space, our projective line, is really geometrically two-dimensional space. And look what happens if I grab that point. If I move to the center, it gets closer to the south pole, and if I move it far out, it gets closer to the north pole. So let me mention one thing at that point. The set of all complex numbers can be geometrically visualized very nicely as a planar situation, but still algebraically we are dealing with a one-dimensional algebraic space, the space of the complex number line on which all those points live. Here is another picture of the situation, which is a photo from a book of Henry Sagerman, where you really see this projection done in a physical way. So here you have this object, which is actually a 3D printed object, and you have a flashlight here, and you really see how this projection takes this object here and creates a well equidistant square grid from that. And one observation that you make from that picture is that to get those straight lines here, what you really need in the original picture are curves. So you really get curved lines on the sphere that project down to the straight lines in that picture, which is something that is very special to stereographic projection. Here is another photo. It's taken from one of our model building seminars at Technical University of Munich, and this photo has been taken by Tim Hoffman. And here you see again a 3D printed device and its shadows under stereographic projection. And here you see a regular grid of circles, and if you look closely you observe that all the things that you project from the sphere down to the plane here are circles on the sphere as well. And this is a very special thing about the stereographic projection. It maps circles from the sphere to circles in the plane. And I mentioned in my list of things I want to show you that circles play a special role here, and one of the reasons for that is really the nature of stereographic projection. So here again you have the 3D animation, and in this animation you see that actually a circle here maps to a circle down in the planar situation. And as a next thing, I want to go away from this stereographic image. We will come back to that in one of the later classes, and now give you a kind of intrinsic explanation why circles are very special in our CP1 geometry. And one of the reasons why circles are special can be traced back to a nice theorem in elementary geometry, and this theorem is called the inscribed angle theorem. And it tells you the following thing: assume you have 2 points on a circle and you have a third point which is assumed to be variable, so it's allowed to move on the circle in an arc that lies above the other 2 points. Then it turns out that the angle that you measure at those 2 lines connecting your movable point to your 2 fixed points here will be a constant, and this constant will turn out to be exactly half of the angle under which the midpoint of the circle sees your 2 points. And since this is a really fundamental starting point for all the investigations that come after this, I want to give you an elementary geometric proof of that, and this is a kind of proof without words. If you stare long enough at this picture, you will understand why this theorem is true, but I will give a few words anyway to that. So you know 2 things. You know that the angle sum in a triangle is 180 degrees, and you know that a half circle is 180 degrees as well. And now you have these 2 triangles here in the picture. You have this triangle, and I've drawn here such an auxiliary line in our figure. And since you are in a circle, you observe that this angle here must be the same as the angle down here, but you know that this angle plus this angle plus this angle must be 180 degrees. So these 2 angles must fit nicely in the gap between those 2 lines. This is just that you get the 180 degrees in 2 different ways. And you can do the same argument for the other triangle, like this triangle. This angle here occurs in this position and in this position, and it has to fit in this gap. And this proves that the overall angle that you get up here must be twice the angle that you get down here. It's exactly what I claimed before. So how does this theorem relate to projective geometry? So let me slightly reformulate what's happening here. So assume we have 4 points, and then this means that whenever you have 2 fixed points, A and B, and you have 2 different points, D and C, that both D and C see the other 2 points under the same angle, let's call it alpha, at least as long those 2 points are both above the line connecting A and B. You get a different angle if C, for instance, moves down to that place. I will come back to that point in a minute. So let's for a moment assume C and D are both above this line. Then we can rephrase the inscribed angle theorem as 2 points A and B on a circle, our 2 points here, are seen from all other points, D and C, on the same side of A and B, so they are on the same side, under the same angle. And now we will turn that into an algebraic statement. And for that, we embed the whole picture in the plane of complex numbers. So these points here are complex numbers, and the vectors that I've drawn here between 2 such points are differences between complex numbers. So if you subtract D from A, you get a complex number that has exactly from the origin this direction here. And now I calculate this quotient here. And you should remember that multiplication of numbers in the complex plane corresponds to addition of their angles. So division of numbers corresponds to subtraction of angles, which gives us an access to this inscribed angle here. So the angle of that complex number that it forms with the real axis is exactly the angle alpha that we have here. And we can do a similar thing for the other angle that we see at point C here, and we get this number. And now the inscribed angle theorem claims that these two numbers here have the same angle, and we can check if two numbers have the same angle by simply dividing them. If they have the same angle, we will end up with a number that is real and positive, because dividing two complex numbers with the same angle, I already mentioned, dividing corresponds to subtracting of angles, and subtracting alpha from alpha gives us an angle 0, and this means a positive real number. So this number that we get here will be a positive real number as long as, well, assume I move C here, as I move C on that arc here. So similar statements hold also if I move C below that arc. So I just claimed this here will be a positive number, and below that arc you actually will get a negative number here. And this comes from the fact, and I'm only a little bit sketchy here, that if point C is placed below, here you will get a kind of counter angle to the angle you measured over there, but I don't want to go into the details here. So, independent from that, you get a negative number here, and actually if you look even a little bit more closely, you will find out that you get a number 1 here, and that you will get number infinity here, and a number 0 here. And if you look at this, this really looks like a projective scale on the boundary of the circle, and actually it is a projective scale on the boundary of that circle, and we will come to that point a little later. I also made a statement here, and it also holds for collinear points. So assume that A, B, C, and D are on a line, and then the vectors that you get between point pairs always point in the same or in opposite direction, which also gives a real number here. So now comes the important observation. The important observation is that what you've written here is actually a cross ratio. And you can, if you fill out all the gaps that are left in my sketchy descriptions here, you can prove the following theorem. 4 points A, B, C, D in the complex projective line are either co-circular or collinear if and only if the cross ratio between these 4 points is a real number. So having a real number is a certificate for 4 points to either be co-circular or collinear. And well, you see that we somehow put co-circular and collinear into one category in that theorem, and this is a natural thing because you can consider line as a circle with a very, very, very large radius, radius infinity. So a line is actually a circle that passes through our point at infinity, and if you look at the stereographic projection, all the lines that are projected from the original number plane onto the sphere will actually really share this one point at infinity at the top of this sphere. So let us take this nice theorem now to further investigate the special role of circles and CP1 transformations. So assume you have a circle, and on that circle you have 3 points, and now we get the following theorem, that when you have a projective transformation, it will map the set of circles and lines again to the set of circles and lines. So whenever you start with a line or circle, make a projective map. This line or circle will again be mapped to a line or circle. And for understanding that, first observe that 3 points uniquely define either a circle, or if the 3 points are collinear, a line. And now take the images of these 3 points and use the fact that the cross ratio being real is a projectively invariant property. So assume you have a projective transformation that maps these 3 points here to these 3 points. Through these 3 points you again get a unique line or circle, and the claim is that all points on those circle from which you start are mapped to the image circle. So just take a generic point on your circle here and map it by your projective transformation. What do you know about this point on the circle here? Well, it has to form a real cross ratio with a real number with respect to the other 3. And if you map it, it will be mapped to a point that is again in a real cross ratio with the 3 image points. And this exactly was our characterization for a point being on that circle, which finally means any point on that circle here will be mapped to a point on the other circle. Let's take that even one step further and write down something that's almost trivial but far-reaching from what we got so far. If you have a CP1 transformation that leaves a given circle invariant, we can determine that by 3 pairs of pre-image and image of points on a circle. So you see, this sounds very, very similar to what we did in earlier lectures with points on a conic. There also we had the situation that the images of 3 points on a conic uniquely determined a transformation that leaves the conic as a whole invariant. Here we get the same idea of concept in the CP1, and we have 3 points and 3 images, and if the 3 images are again on the circle, then this will map the circle to the circle. And what we are heading at is that this map on the circle behaves very similar to what we had if this circle is considered as a conic in RP2, but inside and outside of the circle, these maps will behave very different. And for that, let me start with a little movie of CP1 transformations that leave a circle invariant. You remember we had a very similar thing when we were studying RP2 transformations that left a conic invariant. But here, this transformation that we get here looks extremely different. So one characteristic fact is that all our circles are still circles. Another interesting thing is that this transformation maps things inside out, or may map things inside out. So here you have our original smiley completely outside of the circle, and we will try to understand what's going on as a next point. And for this next point, I will write down a theorem that I won't prove in this lecture. We will prove it in the next lecture, but I want to state it already in this lecture. So consider a CP1 cross ratio of 4 points on the circle, and we know this is a real number. And the cross ratio that you get here is the same as the one that you get when you take the 4 points and the circles and embed it in RP2, not in CP1 but in RP2, and consider the circle as a conic C, and you calculate the cross ratio of those 4 points. So for Co-circular points, it doesn't make a difference if you calculate the cross ratio in CP1 or you calculate the cross ratio on the conic in RP2, you will get exactly the same number, which tells you that both transformations on the boundary here really behave in the same way. And as I said, we will prove that in one of the next lectures. And before that, I want to give you a comparison of those two transformations. And for this, I wrote the following animation, and I have first to explain you what you will see next. So what you will see next are two pictures. The picture on the left is CP1, and the picture on the right is RP2. In both cases, we have a circle. Here it is a circle in the complex number plane, and here it is a unit circle in RP1 considered as a conic. And in both cases, I consider projective transformations, here CP1 transformations and here RP2 transformations, that leaves this circle here invariant, controlled by 3 points. And in what comes next, I will only move this point here and we will observe what happens. So let me start moving that point. And first thing that you should observe is that these two transformations really look different. These are completely different pictures that you see here, but they agree on the boundary of the circle. So if you look at the little marks here for the minutes, they appear at almost exactly the same places in both pictures. Actually, inside the circle, the two transformations don't look that different, but outside the circle, they look very different. Several things that you can observe here are, for instance, that all our clocks that we have in the CP1 picture are really circles, whereas in the other picture, all the clocks, all the images of the clocks are distorted circles, which means they are ellipses or even hyperbolas. Second thing that you can observe, that in this picture, in the RP2 picture, the hands of the clocks still look straight, while in this picture the hands become curvilinear. Then there is some observation that you can make if you look very closely. If you look in the CP1 picture, the angle between the hands is the same in each of the clocks that you see here, which corresponds to what people call a conformal mapping. And in the other picture isn't conformal. If you look at this angle and this angle and this angle, you see they are very different. So let me move on with my journey that I'm doing here and go to an even little bit more extreme situation. And one thing I want to show you here is that it may even happen that you get straight lines in your picture. So a circle may be mapped to a straight line here. Another thing you may observe here is if you look at the 9 here, the 9 in the real picture gets flipped over. So the 9 and the 10 are mirror images. And if you look at all those numbers, you always can read them. So they may get turned around, but they never occur as a mirror image. Let me move on. So now I take again my point and this time move it to the other side. And one thing that you should observe now is in this picture, it may happen that one of those circles gets turned inside out, and so the entire clock resists outside one of the circles, but the boundary of the clock still is a circle here. Let me move on and go to the extreme case where I go through the singularity here, and now you see I flipped over the situation, and in that picture there are several things you should observe. One thing you should observe here, the world got really turned inside out, but look what happened to our hands. Our hands in the original picture really were straight lines. Now they are really arcs of nice circles. Second thing you should observe, you can really still read our numbers here, but here in the inside of the circle, after the singular situation, things got flipped over and you got mirror images here. So let me go one step further and move to the extreme situation where this point here is really opposite to its original position. What you see now is that in the picture of the real projective plane, things look almost as we had in the starting situation. Well, almost, but not really, because the entire image has been reflected at the x-axis here. So you see all our numbers here are really mirror images of the numbers that we saw so far. In the other picture, it got different in an interesting way. Things have been turned inside out. So what was the interior of the circle now became the exterior of the circle, and the exterior got mapped to the interior of the circle. And still you can read the numbers here. You can even read the quarts over here. And if you look closely at the numbers, something very strange happened here. So for instance, the 12 and the 6 are readable in a proper way. And to get there, the numbers got rotated. So here the 3 is in an upside down position. It got rotated by 180 degrees. So I really encourage you to contemplate on that picture and how it can happen that you get these strange rotations of the numbers here. So I want to end my survival package for CP1 by two remarks on projective transformation. First remark is, well, we saw a projective transformation in CP1 is actually a multiplication by a 2x2 matrix. If we want to do this thing in standard embedding, we can say, well, we have one complex number in the standard embedding and map that to a new vector. And then we can turn this new vector, which has two entries, again into a number in standard embedding by dividing by set 2. And at least if we don't divide by 0 and if we don't have infinite points here, we can express this as a function that even doesn't need the embedding in the projective plane. It's such a kind of rational linear mapping that we get here. And these mappings have a name. They are called Möbius transformations, after the great geometer August Ferdinand Möbius, who can also be considered as one of the pioneers of projective geometry. He was the one who really had a very early form of homogeneous coordinates, as perhaps I would say the first mathematician ever. And he also dealt with the complex plane. And this kind of transformation here, this Möbius transformation, really pops up in several branches of mathematics. So it's, for instance, important also in complex function theory. And whenever you see that expression in complex function theory, you should immediately be reminded what you're actually doing is a transformation in the space CP1. So there is one last point that I had on my list of things I wanted to tell you, and it's about the non-trivial field automorphisms in the complex numbers. So the non-trivial field automorphism is the one that sends I to minus I, or if you extend it to the complex number plane, it sends z to the conjugate of z. And this transformation here cannot be covered by any Möbius transformation. So no matter how you choose A, B, C and D, you will never get such a conjugation. And actually this was the deeper reason why we always had non-reflected images of our numbers of the clock that I showed you before, because this transformation here, this makes a mirror reflection, and in my book I call transformations that involve set conjugate instead of that, I call them anti-Möbius transformations, and they make all the reflection parts in CP1 transformations. They still have the property that they are so-called harmonic maps. So if you have a quadruple of points which is in a harmonic situation, like having cross ratio -1, after such a map they will still, as in the Möbius transformation case, be in harmonic position, but they introduce some reflection, and as special cases you get, for instance, the reflection in the real axis and also the reflection on the unit circle, where perhaps I should explain what reflection on the unit circle is. If you have the unit circle with the center of the coordinate system here, then a point is mapped by reflection in the unit circle to a point which is on the line connecting the 0 to the image and pre-image point, and there is a certain relation between the about the distances of those points to the origins that I don't want to mention here. Instead, I want to give you, as the end of this lecture, another movie that shows how anti-Möbius transformations act. So here I have an anti-Möbius transformation that maps the boundary of the clock again to the clock, and if you look now, now the picture has been reversed along the real axis, and all our numbers here are really mirror images. And now I move the transformation a little bit, and you will observe that in all the pictures that we have here, you have mirror images of the numbers, except for that everything is exactly as it was in the case of Möbius transformations. So for instance, when I move this situation to the situation where this point is exactly opposite of its original point, you get the reflection in the circle, which turns the world inside out. So we will use all these things, all this understanding about complex coordinates in our next lectures to get a deeper understanding of how we find other geometries within projective setups, and for that we will have to somehow merge the RP2 world and the CP1 world in an interesting way, and this will keep us busy until the very end of our class for all our next video lectures. I hope you stay tuned. See you there.